This program is brought to you by Stanford University. Please visit us at stanford.edu.
All right, so I think, first of all, for the peanut gallery, why don't you stand up and just remind them who you are with your name. So you start to get faces and connected. So Sasha, why don't you stand up?
Sasha.
Sasha. Ben.
I'm Baby K.
Shashank. David.
All right. So that's a piece of the peanut gallery. And of course you know Max. Let's give Max a hand. How'd he do? Huh? He's actually never seen an oil refiner in his life, so I hope he did all right. So what'd you learn from that lecture?
That colors don't photocopy well.
Colors don't photocopy well. The notes suck. I understand that.
Draw boxes.
Draw boxes and connect them. So you learned a little bit about flow sheets. And flow sheets are really very important in chemical engineering and in design in general, of connecting what are called the unit operations that perform certain functions where mass and energy is being transferred between and among them. You use it as a bookkeeping tool. And it's sort of a key attribute that will come up again and again in the class as we move through the quarter. So the first thing that you've really learned in the class is something to do with flow sheets, how they're constructed, and the purposes to which they'll be used will become more apparent as we move through the class. Now, you might wonder, why am I, a Stanford student, going to have to sit through a lecture on units? Because I know all about units. Well, maybe you do and maybe you don't. And so let's find out. This is kind of a little sick cartoon, converting feet into meters. And one of the really interesting things about units is why we have them and where'd they come from. I grew up accepting that it was the force was pounds and the mass was pounds and the length was feet and time was seconds. And I think in perhaps the way you folks have been educated, you're more used to the metric system than I was when I was your age. In fact, it existed, but we never used it. And the metric system actually is the sort of the legal system of units in this country, although still most engineering companies and concerns don't use it. And of course, one of the problems is all the equipment in this country is tooled to feet and inches and not to the metric system. So any of you who work on cars, like I used to work on cars, now I can't work on cars. Nobody can work on cars because it's just a computer and you throw it away when it stops working. I actually used to take cars apart and put them back together, and I sometimes had European cars and sometimes had American cars, so I had two sets of wrenches, metric wrenches. They never quite fit, just off just a little bit, metric wrenches and American English unit wrenches, as it were. We and the British are the last holdouts on Earth that use this system, and it gives rise to some problems, and I want to tell you a little bit about some of the problems. But first, let's talk about where did some of these units come from. It turns out that the yard, roughly 3 feet, goes back to an iron stick that King Edward had. The inch was 3 barley corns, of course round and dry, stacked up against one another. That's an inch. During the French Revolution in 1793, I think Napoleon got sick of this, and actually, they hated the British, so they wanted to do something different. And they decided that they developed this base 10 system, which really made sense, a base 10 system. And you needed a unit of length, so they declared it to be 1/10,000,000th the part of the distance from the North Pole to the equator, measured on a line, of course, running through Paris, the meridian. Now the problem is the French couldn't go outside their country to make this measurement because they'd get beat up. This is like this is like David Kennedy giving you history. They'd get beat up. So they had to measure this meridian only within France, and then extrapolate it to the equator and to the North Pole. And they did that, and they actually got the distance within about 2,000 meters, which is about a mile, which isn't bad when you're limited to how far along this meridian you can actually make the measurement. And so that's where the meter came from. That is not the standard that's used today. I'll talk a bit about that later, but that's how it started. And it's roughly a little bit more than 3 feet. Others are the cubit from the Old Testament, from the elbow. Now that we're taping this, I can't actually demonstrate this, but you can imagine the elbow to the tip of your middle finger. If you want to demonstrate that, you can, because I don't want to go see the ombudsman. And that's probably where, road rage came from. There's the hand or the span. So the hand was this distance, and the span was that distance. The hand was a unit. Paces, Roman soldiers' measurement of 2 strides. So that's the distance between when your same foot hits the ground again. So boom, boom, there. That's a stride. Generally about 6 feet or so. The fathom, the distance between outstretched arms. An acre, this is cool. The area a man, not a woman, a man can plow in one day with 2 pair of male oxen. So it's a very sexist unit. That's where an acre came from. I mean, it's really stupid. And a carat is from the Arabic word carab, which is a small bean, and it represented a unit of weight. So these are really obscure. I have some others here. The inch was also the width of a man's thumb, also the length of a forefinger from tip to the first joint. A foot was the length of a man's foot. A yard was the distance from the tip of a man's nose to the end of his outstretched arm, also 3 times the length of the foot. See, these are pretty subjective units because obviously not everybody has the same length of arm and same foot and so forth. But it's hard to believe, but societies and villages and so forth did exist with these units of measurement. Now, do you have any idea why the railroad gauge in the United States is 4 feet, 8.5 inches? That's the distance between the tracks of a standard railroad in the United States. 4 feet, 8.5 inches. Where do you think that came from? It's kind of weird.
Is it the height of a short laborer?
The height of a short laborer? Who would they lay them down on the tracks and then run over them? I mean, that was...
measure of spacing, Lie down, oh, we're good. Okay.
Lay down, oh, I see. So that was how they did it, with little people that were 4 feet and 8.5 inches. Well, that was good. I like that. Not quite right. So why is that? So I'll read this to you. Well, first of all, the gauge in the United States, 4 feet, 8.5 inches, is because that's what the gauge is in England. And that makes sense, right? Because England invaded us. By train, that's right. And started building train tracks here just like they had them in England. It's a long bridge. Now, why did the English build them at 4 feet, 8.5 inches? Because those first rail lines for freight and passengers were built on the models of those who preceded them and built pre-railroad tramways to get up into the mountains. And so that was 4 feet, 8.5 inches. Now, why did they use that? Well, they used that because the people who built those tramways used the same jigs and tools that they used for building wagons that used that same wheel spacing. So the wagons that had been built that preceded these trams had been 4 feet, 8.5 inches as well. Now, why were the wagons 4 feet, 8.5 inches that preceded the trams that preceded the railroads? Well, if they tried to use any other spacing than 4 feet, 8.5 inches, the wagon wheels would break because they wouldn't fit in the ruts that preceded them that were already there in England and France of what were the roads in those times. So there were ruts. And they built the wagon wheels 4 feet, 8.5 inches to fit into the ruts. Now, where'd those ruts come from? Who invaded France and England? The Romans. And the Romans used what to get around on? Chariots. Now the chariots had wheel spacings of 4 feet, 8.5 inches. Now why? Because they were pulled by 2 horses, and the distance between 2 horses' asses is 4 feet, 8.5 inches. And that's why we have that today. So it was dictated by 2 horses pulling a chariot back 2,000 years ago. Now, this did other things. The main booster rockets, the solid booster rockets on the space shuttle, are made by Thiokol, and they're made in Utah. And they have to be shipped to Cape Canaveral because the shuttle doesn't take off from Salt Lake City. The constraint on the diameter of the solid rocket casings was dictated by what? Essentially, Theo, you're right. But one step before that, where did these things have to go through? Rail tunnels. And so essentially it was dictated by the width between 2 horses' asses as well. The whole space shuttle program.
But actually it has to be, it's slightly narrower than that because it has to be shipped in a bulletproof boxcar because it goes through the South and apparently it's a pastime there to shoot at passing trains.
I think they take the northern route through New York where it's even worse because that's where you come from, right?
Oh, that's good.
You like that? There they just hijack them and turn them into scrap.
I'll vouch for Southerners shooting at trains.
Oh, now we have admissions and confessions. So it's really, I think, interesting to try to understand how the English or the American engineering system has come about and why we have the units we have. There's 2 kinds of systems. There's the absolute system and there's the gravitational system. So let me take the absolute system first. Here's your basic units that define a unit system. You have to have a unit of length, time, mass, temperature, expression of force, acceleration, pressure, energy, power, and so forth. And in the absolute systems, you have the metric or CGS system, the MKS or SI. Does anyone know what SI stands for? French? System International, yeah, international system. The FPS, the foot-pound-second system in English. These are all called absolute systems. And the reason they're absolute systems is because what's defined in them are the units of length, time, and mass right out the door. Whether it's gram, centimeter, second, kilogram, centimeter, meter, second, or pound, mass, foot, second. These are all defined. And everything else, the force, acceleration, the pressure, energy, power, are all derived. They're derived as combinations of those 3 core units. And they're derived through the use of Newton's law, F equals ma. And you'll see that there's this little thing on the bottom here called G sub c. Well, I'll explain that because G sub c is the fudge factor that allows the gravitational systems to work. Now, let's talk about the absolute systems again. So let's just take the MK system, which I think you know it best. If you plug mass of kilogram into Newton's law, and you plug acceleration, which is what? Meters per second squared, you get a force unit. And so the force unit is what? It's kilograms meter second squared. And what do we call that? We call it a Newton. So the Newton is a name that's derived. It's what's applied to the set of units that arise from using Newton's law to determine the units of force. G sub c in this system is simply dimensionless 1. You don't really need it. And acceleration follows, we have that as meters per second squared. Pressure, which is force per area, newtons per meter squared. Energy, which is what? How do you get energy units or work units? Force times distance, right? So it's a Newton meter, and we call that a joule in this system. And power is a watt, which is joule per second, energy per time. Okay? So that's where the watt comes from. And in the CGS system, which you probably don't use as much, the force unit is called a dyne, energy unit is an erg, power is ergs per second. In the foot-pound second, or English absolute system, it's pound mass is the mass, second is time, foot is length. The force, which you get from Newton's law with G sub c equal to 1, is called a poundal, much like in the MKSS it's called a Newton. You've probably never heard of a poundal. Nobody uses it. So we cross this out. But the English do this just to show that they have an analogous system to the MKS system, which nobody uses, not even the English. Instead, the English use the gravitational system, which is what we also use. Now, in the gravitational system, interestingly enough, what's defined is the length is foot, time is second, and force is defined as the pound force. So what is undefined? The mass. And so where do you go to get the mass? You just back solve Newton's law. Mass is equal to F times G sub c over A. And you'll get the units, and that's called a slug. Now, actually, when I went to school at Berkeley in the 60s, we actually had problems where we had to use a mass called a slug. I thought a slug was something that's squishy and crawls around, on the ground that you pour salt on and watch them foam as you extract their insides out from osmotic pressure. But and you'll see the acceleration is a foot per second squared. The pressure is a pound force per foot squared. Energy is pound force times foot, force times distance, and so forth. Nobody uses this. Then there's the American engineering system, which is what we're really familiar with. And now this is really screwy. It's really screwy because in the American engineering system, for instance, if you go to the market and you buy a pound of bananas, are you buying a mass of bananas that weigh 1 pound? Huh? But how do you determine it? Where do you put the bananas? On a scale. And the scale is measuring what? A force. And so the British said, since we buy our bananas and we put them on a scale and it weighs a pound, we don't want to say we've bought a pound force of bananas. We're going to say we bought a pound of bananas. So why don't we make the pound force and the pound mass the same on Earth? And then we don't have to worry about this. You don't have to go to the grocery store. Hey, you can't charge me for a pound mass of bananas when I actually measured a pound force on your scale, and so on and so forth. You can complain about the calibration and the spring constant and so forth, and then just take the bananas and walk away. So how do you make the pound mass and the pound force the same and still be consistent with Newton's law? Well, first of all, the acceleration that we're talking about is 32.2 feet per second squared, because that's the acceleration of gravity. So that has to go in for A. All right? And we said that pound force is on the left and pound mass is on the right. And you've got 32.2 feet per second squared sitting here, which means you need to dream up a constant, G sub c, which is equal to 32.2 pound mass foot per pound force second squared, so that when you stick it into here, this is dimensionally consistent. So can you do that in your head? If you put 32.2 feet per second here for A, and you put this G sub c down here in the denominator, you will see that what Newton's law gives you is that 1 pound force equals 1 pound mass. And you might say, that's pretty contrived. You're absolutely right. And so there's no denying that. And you've probably never used G sub c. You've probably never really thought this through, because you just merely put a pound here and a pound there. But really what you should be putting here is a pound sub F for pound force and a pound sub M for pound mass when you use this, and stick in this G sub c, this gravitational constant. So the reason we get tangled up in the American system is, unlike this, where you say the Newton is the force and kilogram is the mass, we've demanded that pound be mass and pound be force. And to do that, to be dimensionally consistent, you have to have this conversion constant, G sub c, in here. Now, if I were to ask you, what's the relationship between a Newton and a pound force, how would you do that? Yeah, Red?
What's the R for?
The R is the temperature unit.
What is it?
Oh, R means Rankine. It's an absolute, it's a temperature scale like Fahrenheit, but it's displaced by about 200 and some degrees, or 500 and some degrees, I think it is. We never use it. But it's a Fahrenheit, it's a degree that has separations between the degrees that are 1.8 times that of the separation that you have in the centigrade and Kelvin scales. So if you look at a centigrade thermometer, it goes from 0 to 100 degrees. And if you look at Fahrenheit, it goes from 32 degrees to 212. Well, 32 minus 212 is 180, so it's 1.8 times. The markings, if you will, on a Fahrenheit thermometer are 1.8 times for every one marking in a centigrade scale. So if you were to convert from centigrade to Fahrenheit, you just wouldn't multiply by 1.8, but you have to take into account there's 32 degrees that separate 0 degrees centigrade from 32 degrees Fahrenheit, both of which are freezing. Don't blame me. I didn't do that. But that's the way it is. Now, you know the difference between the centigrade, the Kelvin scale and the centigrade scale is how many degrees? 273.2 or something like that. So this, you know, if this is absolute zero, it's zero. If this is absolute zero, it's minus 200 and whatever it is, 72 degrees. It's kind of a pain in the butt, but that's the way it is. But even today, I have trouble with centigrade. You know, someone says it's, 30 degrees centigrade out. It means nothing to me. You know, I think it's hot, but the one I remember is always 20 degrees centigrade is 68 degrees Fahrenheit. And do you know where the Fahrenheit and centigrade scale are equal? Negative 40 degrees. That's good.
Does 0 Fahrenheit have a meaning?
Yeah, it's 32 degrees below freezing. That has meaning. All right, so let's just answer the question of the relationship between pound force and newtons. So 1 kilogram is equal to how many pound mass? Do you know? 2.2 pound mass. And so it's always helpful to put the pound mass there. So using Newton's law, if we take a kilogram and we accelerate it in Earth's gravity field of 9.8 meters per second squared, we get 9.8 newtons. And if you take 2.2 pound mass, the same amount, and accelerate it in Earth's gravitational field of 32.2 feet per second squared, And then, of course, we have to put, what am I writing here? This is the fudge factor. This is G sub C. So if I cancel my units, this is equal to 2.2. You can't see that, can you? 2.2 pound force. So I'll write it down here. Because this is pound force and this is newtons, according to. So what's the relationship between a newton and a pound force, roughly? One newton equals how many pound force? It's about 0.22 pound force. So how do you remember that? Remember, this is about 1/4 pound, right? 0.22 pounds. So a 1/4 pounder at McDonald's, you can call it a Newton burger. And that's how you remember. Now, if you don't like that because you don't eat at McDonald's, I don't eat at McDonald's anymore because I had a hamburger about 15 years ago and there was a piece of cow skull in it and I cracked a tooth and had to have the tooth replaced. And because they don't put the meat in there, they put everything else but the meat in there and they grind it all up and put it in a puree and then serve it. And so I can also remember this as a newton is about the weight of an apple because it fell from a tree, remember, and hit Newton on the head. So that's how you can remember. Now, why is that important that you know these things? Can you read this? This is a headline, Thursday, November 11th, 1999. Program failed to detect error in Mars orbiter. You remember this? You in 1999, what grade were you in? Like first grade? Or sixth grade? The loss of the $125 million Mars Climate Orbiter spacecraft could have been avoided if NASA's checks and balances had detected an English metric conversion error that doomed it even before launch. So this spacecraft goes up. It's got this $125 million Mars orbiter. It was to be injected into Mars orbit and take pictures of Mars. A high school classmate of mine at the Jet Propulsion Laboratory working for NASA was the program manager. He's now selling pencils in Lower Slobivia on the street corner. And what happened to him? See, here's another one. Metric mix-up may have doomed Mars orbiter. The orbiter was made by Lockheed Martin in south of Denver, Colorado. The thrusting instructions for it were printed in thrust force, in pound force. When it got to JPL and they shot this thing up and they were sending commands to the little thrusters on this as it's making its way to Mars, they read that table as newtons. So all the thrust commands were off by a factor of about, if you invert this, about 4.4. So this little spacecraft that sees Mars is going, oh, we're good. That's a big, another big hit. But Mars is over here. Oh, and they're wondering what the hell is coming up from the ground station here. So by the time it got to Mars, it just blasted right through the atmosphere and splatted a big old splat right on the face of Mars. And there was our $125 million Mars orbiter, which didn't even make one orbit. Now they hit Mars, which is a good thing, but this thing was going about 30,000 miles an hour faster than it should have been going by the time it got there. So that was a huge problem of a metric conversion gone sour. Too bad. Poor Glenn Cunningham, I remembered him. He went to Berkeley with me too. Wasn't that great a student, but he did end up in government service for a while until that happened, and then it was over. Problem was he was a double E. And see, double E's didn't take E20. They didn't get it. They hadn't heard the units lecture. You see? You've heard the units lecture. You're not going to do this. So there's lots of other, there's some other base units, moles, not the kind that crawl in the yard, electric current, the amp, light intensity, and so forth. So there's other base units that sort of fill out the panoply of units. And then there's derived units. And derived units are always made up of the base units. So the base units, there'll always be 3 of them. It'll either be mass, length, and time, or as in our system, it's going to be length and time and force, from which the mass unit is derived. So volume is made up of the length units, force is of the mass times acceleration, pressure is force per area, energy and work we've talked about, and power, the watt. So those are derived units. They're made up of those fundamental base units. Now, you've all have heard of horsepower. What's 1 horsepower?
746 watts.
746 watts. Now, isn't it interesting that you related it to watt? Because you know who invented the horsepower unit? James Watt, in the late 18th century. Now, how do you define 1 horsepower? I mean, you don't say it's 746 watts. I mean, that's going in a circle. Does it have something to do with the power that a horse can exert? I mean, you would think so.
A horse can ride over a day.
Okay, how much the horse can ride in a day? Is that 1 horsepower? I can never remember. It's nuts. It's the power it takes to raise 3,300 pounds, 10 feet in 1 minute. Because you could take a horse and pull this thing up, and it could do it in a minute. Can you imagine? What if he'd started like with 10 tons and the horse, now take some weight off. And finally, you know, the horse goes like this. Now, it went through a lot of horses to figure this out, it says here. Now, horses have changed. They're weaker now. And actually, you know the Mythbusters, that thing on E! Channel or something? It turns out that modern horses can only generate about 3/4 of a horsepower. Because they actually showed on the Mythbusters, they put the 3,300 pounds and the 10, and the legs were going, finally it's on its belly, and then the horse is upside down. And it died. It died right there on Mythbusters. And so, yeah, little horsey. What they did, they stuffed it and put it on a merry-go-round. And so here's all these prefixes. Normally, we'd only have to know nanometers and micrometers and millimeters, centimeters, decimeters. No one uses deca and hecta. And kilometers we use, gigameters. We don't use that too much. But we're starting to get into tera and peta, in computers, right? Terabytes, and we haven't got the petabytes yet, but we're at terabytes. We're beyond gigabytes. And down here, 10 to the minus 18th is atto, femto, and pico. We're kind of working in this area right now in fast chemical reactions. So we've almost used 10 to the minus 18th to 10 to the 18th. That's 36 orders of magnitude of units. It's kind of interesting. So let me just work through a couple of units problems for you. The first one is pretty dumb. It's what's the difference in weight in newtons of a 100-kilogram rocket at a height 10 kilometers above the surface of the Earth, where the gravitational pull is a little less than is on the surface by not much, 9.76 meters per second squared versus 9.8. Use F equals ma, and you find out the difference is 4 newtons, and we know that 4 newtons is about a pound. So for those of you that are interested, the rocket weighs about a pound less. Here's a more interesting one. Santa Clara County produces, that's the county we're in, by the way, produces about 1.66 times 10 to the 6 tons per year of mixed municipal refuse. Okay, so that's about 1.5 million tons of mixed municipal refuse. This is the garbage you throw out. Now there was a process called the Union Carbide Purex process, which could take this material, the stuff you put in your garbage, and convert it into a synthetic natural gas called syngas, which has a composition of about 24% hydrogen, 40% carbon monoxide, 25% carbon dioxide, and 5.6% methane, plus some other gases. Now, this gas, actually, it can be burned, like natural gas can be burned. And the question was, what percentage of the natural gas demand supplied by Pacific Gas and Electric to interruptible customers would be met? So what's an interruptible customer? An interruptible customer is a person that buys natural gas from PG&E and burns it, but is willing to be the first person to be shut off when natural gas demand skyrockets and PG&E can't supply all the natural gas. And as a result, they pay less for it. So these are the people who dry fruit, people who have very large furnaces, large consumers of natural gas. They're willing to pay less for their gas, but also be the first ones to be turned off if they have to be. So the thought here was, and this was actually a project I ran with a bunch of students a number of years ago, was could we take all the municipal refuse and turn it into a burnable gas that we could sell to interruptible customers? Now, why not to everybody in their homes? The reason is, look at this stuff coming into your home. 24% hydrogen, 40% CO. Death. You either blow up or you suffocate or both. And so PG&E would not ship this into people's homes. It's okay to ship methane in there. Because see, with methane, what happens, even though it catches fire, it can conceivably blow up, not nearly as bad as hydrogen. But whereas CO essentially suffocates you because CO binds to hemoglobin and displaces oxygen, so you're just sitting there, But with methane, it's not nearly as bad. That's just toxic. And then it knocks you off. So you know how methane smells? Methane doesn't smell at all. But the reason it smells when you turn on gas, so that you know it's there, is a small amount of sulfur compounds are put in, which really smell bad. And that's what's injected into methane, so that PG&E can say in lawsuits that you should have smelled it. And you died because you couldn't smell. I mean, you could have had a cold, you see, and you couldn't smell it. And then you die, and that's it. So what percentage of the natural gas demand? So here you are, an interruptible customer, and PG&E may shut you down. We're going to come in here as chemical engineers. We're going to sell you this union carbide Purex process. We're going to sell you this gas because it's an industrial setting, and it's okay if you die at work, but not at home. And so what is this equivalent to in tons of coal and barrels of oil? Just to kind of give you an idea of how much energy is stored here. So here's what we're going to give you, the heating value of the refuse. So you get 10 to the 7th BTUs per ton. Now BTU is a measure of energy. A standard cubic foot of this syngas is 310 BTUs. A standard cubic foot of methane is 1,000 BTUs. So this stuff has a heating value which is about 1/3 of that of methane, but it still has quite a bit of heat value to it, 310 BTUs. Here's what the refuse provides, 10 million BTUs per ton. Here's a barrel of crude oil. A barrel of crude oil has about 5.6 million BTUs in it. A barrel of crude oil, remember, is 42 gallons. That's how much is in a barrel of crude oil. So let's remember these numbers because we'll be doing some calculations with them right now. And we're going to also ask how much coal this is equivalent to. So a pound of coal is 12,500 BTUs in energy value. Now this process that we've all invented and that we're selling operates at 24,000 standard cubic feet of syngas is made per ton of solid waste, not waste. So this is how much syngas we can make from a ton of solid waste. And here's the interruptible gas demand we're trying to meet. 29 times 10 to the 9th standard cubic feet of methane per year. This is what our customers are using. The question is, when we convert this municipal waste into this gas, how much of this gas demand can we make? So first of all, what's the efficiency of our process? We know how much heat value there is in a ton of municipal waste. And here we have 1.66 times 10 to the 6th, that's tons per year municipal waste. We know that we can get 24 times 10 to the 3 standard cubic feet of syngas per ton of waste. We know this is the heating value of syngas from the previous page. We know that this is the heating value of methane from the previous page. And here is the gas demand. Times 100, 43%. So what is the efficiency of the Purex process? It's right down here. By the way, 43% means what? That's the percent of the demand we can make. In other words, if we took all the municipal waste, turned it into syngas, we can meet almost half of the interruptible customer's demand through this conversion process, through this plant that we have. So it meets 43% of the interruptible demand. Do you see how I made these lines, horizontal, vertical lines? I would really suggest that when you work engineering problems, you do this. Because the reason you do this is this allows you to cancel units, years with years, tons with tons, cubic feet of syngas with cubic feet of syngas, BTUs with BTUs. Since this is coming out as a percentage, it should have no units. All these units should cancel. Believe me, you can really tell. I'm working a problem, and I'm trying to figure out the speed of a bullet. And I work the problem, and it comes out to be inches per parsec. Now, you know that's not right. You're looking for something like feet per second or meters per hour. So you say, okay, I did something wrong because I took E20, and I learned the way to set up my problems and cancel all my units. Now, you may think this is some kind of brain-dead exercise, but be my high school buddy Glenn Cunningham selling pencils in Lower Slobovia because they didn't get it. You know, you'll be glad you took this class and you do it right. Now, what's the Purex efficiency? Well, this is how many standard cubic feet of syngas per ton that it makes. Here's the heating value of the syngas. And what is this number? That's the amount of heat in the material, amount of energy in the material. And this is the amount of energy we make with our plant. So we're extracting what? About 74% of the energy that's in the trash. So where's the other 26% going? Process energy, but where do you think it goes? Global warming. It goes out into it heats up the world, right? Just like your car. Your car is about 15-20% efficient at best. That's why you have a radiator in your car. That's why you cool it, because it's putting out all this heat. Now, that can be good. I was on a consulting trip. I'm in Steamboat Springs trying to get to Salt Lake City. I got a rental car. I'm on Interstate 40. Not Interstate, just Highway 40. I need breakfast. I go in and get some Jimmy Dean sausage. Duct tape it to the manifold of the front end of the car, put the hood back down, drive 100 miles, stop, open up the hood of the car. My Jimmy Dean sausage is all cooked. Now, that's making use of the heat. That's called heat recovery. All right? So how many hopper cars of coal is this? You know, it's kind of interesting. You can't quite picture what 24,000 standard cubic feet of syngas is. What does it all mean? Let's put it into hopper cars of coal. So here's the density of coal, 50 pounds per cubic foot, and a hopper car, 2,328 cubic feet. How do you find out what the friggin' volume of a hopper car is? How would you find that out? You go to Perry's. Don't ever forget this. You don't go to Google. You don't go to Mozilla or Fire Farm or whatever those things are. You go to Perry, Chemical Engineer's Handbook, and you look in Perry's. Perry's is not like the Bible. It is the Bible. And you look in the index, and you find between pumps and reactive voltmeters. You come down here and you look, railroad cars. You find me a handbook where you can look up railroad cars, Perry's. All right? And actually railroad clearances. So let's turn to page 726 and see what we find in Perry's. Perry's is a very nice book. You should all have it. Have it on your bookshelf. Take it to the dorms. Take it to football games. And you now turn to page 725, and there's pictures of railroad cars. It's not just a railroad car, it's the flat car and the gondola, and here's the hopper car. It even shows you how big the hopper car can be, how long it is, how wide it is, how high it is, and you come down here, type of car, hopper car, you come over here, there it is, level, full capacity in cubic feet, 2,328. That's where you get these kinds of numbers. All right? Yeah? Can we look up a chariot? You can look up a chariot. I didn't bring my early edition of Perry's, but I'm sure the one that came out in 10 AD must have had it in there. They do modernize it from time to time. So here we have a density of coal, and we've got the hopper car. So here is the syngas, 24 times 10 to the 3 standard cubic feet of syngas per ton. Here's the tons per year of municipal trash. Here's the heating value of the syngas. Here's the heating value of coal. Here's the density of coal. Here's how much a hopper car costs. Now, why did I divide by 0.74? That's the efficiency, right? So some of that coal is going to be, I got to take into account the coal that's not going to be useful to me. Divide by 0.74, 11,471 hopper cars per year, which is 31 hopper cars per day. Now you can picture a train with 31 little cars full of coal. That's what this thing is going to do. See, it kind of says, hey, I get that. Now I have a picture in my mind of what this can do. So how many barrels of oil is this equivalent to, this amount of energy? Same thing. Do the same calculation. 3 million barrels of crude oil per year. Now let's put this into perspective. 3 million barrels of crude oil per year. That's kind of a tough unit. You might think that's a lot or a little, but let me tell you, when the Alaskan pipeline was flowing at full capacity, which it no longer does because the oil fields are running out of oil, it was flowing between, I think the maximum was close to 2 million barrels of crude oil per day would pour out of that pipe. So this may not seem like a lot. It's 3 million barrels in a year. But that's what the energy is in the waste that gets thrown away in this general geographic region, what it's equivalent to. But the fact is that we could meet almost half of the interruptible customer demand was actually quite looked upon as quite an interesting result. But of course, there's an economic consequence to this, isn't there? You got to build the plant. And then you got to pay for the plant, amortize it and depreciate it, and try to recover some of your costs. So you'd have to think about the long-term viability of this against natural gas rates as they may be escalated in the future. Now, one of the things I'm going to do when we get to the energy part of this class is I'm going to bring in my PG&E bill and show you how shafted I get by these greedy people. And
Are you up in like the top tiers of electricity usage?
Beyond the top tier.
Right.
We're in like the hog part of it. And I don't know what it is. I think I know. I think it's my wine refrigerators. I don't think they're real efficient. And they grind away, you know, because the wine needs to be kept cold, right? Because after I teach this class, I need therapy. And I go home and I seek it.
There's a lot and a half of solar cells you can buy for half of market cost if you want.
I called up Solar City. I said, bring solar cells to my house. And the guy came out and says, you can't. He says, you don't get enough sun here to fry an egg in 10 years. And the thing is, you know, when we built our houses here on campus, we were building them in open fields. And so I went down to the nursery and I bought 100 redwood trees. I said, it'd be nice to have some redwood trees. And I planted them about 6 inches apart. Well, these things now 100 feet tall. They're about each 3 feet in diameter. And I now have this redwood hedge, which goes around and goes up. So we're like Ewoks. We live in this little village that we can't even see out of. I mean, every once in a while the sun comes down. Other than that, our eyes are getting smaller. We're like turning into moles. I mean, we don't need to see anymore because there's no light. So the Solar City guy went away, and I said, you don't know anything about solar cells anyway, so get out of here. And I sent him away. So do you know there's never been a solar cell made that's produced more energy in its lifetime than it took to produce it? Think about that. Wind energy. You a big fan of wind energy, are you? Figure out how much energy went into those big steel masts that hold that go into the transmission, that go into the maintenance, that go into the power, that lock onto the grid. Wind ain't all that free. How about ethanol from corn? Yet the silliest thing we have going out there. Did you know that the carbon footprint of ethanol from corn is larger than the carbon footprint from turning oil into gasoline? Now you say, why is that? And wait, you got the little corn plant that's sucking the CO2, you burn it, you put the CO2 out, it sucks it back in again. It must have no carbon footprint. You know where all this stuff's being grown? 95% of it is being grown in the Amazon Valley, where they're chopping down the rainforest to grow corn. And do you know that the rainforest on a per acre basis is about 10 times more effective at sequestering carbon dioxide than is corn? So right away, you have a big inverse carbon footprint, right, by having put this plant there that didn't grow there indigenously. So when you think about all these alternative energy schemes, you have to think what we call about the whole energy balance. All the energy that goes in to get you to where you get the energy out, plus how efficient you use that energy, and what you return back into the atmosphere. And then you close that loop. And then you ask the question, well, was that an efficient process? Did I really reduce the carbon footprint? Now, you're getting close to it with some forms of grasses grown in some parts of the country, but not if you're displacing a crop that already grows there. It's like these people thought that all this corn is going to be growing on asphalt. You see, and there was nothing else there, and there was no carbon sequestration there going on. But people typically aren't growing the corn in old drive-in movie lots. They're displacing something else. And in this case, also displacing a food product. 1 gallon of corn ethanol equivalent what goes into it can feed a family for a year. I mean, it's kind of mind-boggling about how this is all evolving. And it's all because of the government who's here to help you, who then decides, since they can't make any money doing this, we'll subsidize these people. So we'll pay them part of what they can't make because they can't sell this stuff unless we tell them to sell it, and then we have to give them this money so that it makes it worthwhile for them to do that. So it's all propped up on this artificial economy. They all look to Brazil and they say, hey, Brazil, they put ethanol in their gas tanks there, and they run 25% of their fleet of cars on ethanol. Yeah, it's true, they do. Banana Republic. They tell you, you do it. What if you have no choice? Boom, pop you off, just like that. Well, you don't need any gas, right? So that's a little history lesson for today, and a little bit on energy. We'll talk about that from time to time. Don't get me going on it too much, because it makes my blood boil a little bit. I'm not really all that fond of fossil fuels either, but we're still waiting to come up with a better alternative to some of the things. These people are building ladders to the sun, stuff like that. That's pretty cool. And piping the sun's energy through glass pipes. Have you seen the stuff that's going in the Mojave Desert and the solar stuff down there? Did you see they just did this? A big tower, big can of water that they're going to heat up, and then all these mirrors around it. They turned that sucker on, you know what happened? They just vaporized the whole thing. This thing went poof. And there's nothing but melted wad of steel. I mean, who's making the calculations? You take this class, that will not happen to you, okay? Let's get out of here. See you on Wednesday.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.